Hello, I'm James Reel, and I'll be presenting a method for maximizing throughput in a sharded blockchain ledger using transaction pricing. This is joint work with Jonathan Ward and colleagues at Fetch AI. So I'll start by talking about the scalability problem, giving a brief overview, and discussing sharding, which can be thought of as parallelizing the validation of transactions as a possible solution. Then I'll introduce some metrics related to shard and transaction efficiency that can help to design a transaction pricing policy that maximizes throughput. The main result is that this policy gives the agents an incentive to make efficient use of the shards. So we can show this both analytically, and I'll also demonstrate this with some simulations on small to medium-sized networks, and then I'll conclude. Something that is quite well known in the blockchain community is called the scalability trilemma. And it says that we can generally prioritize only two out of decentralization, security, and scalability. So to have good scalability, we need to be able to process a high volume of transactions in a relatively short period of time. But the most well-established blockchains like Bitcoin and Ethereum have a peak throughput of about 7 to 15 transactions per second. So sharding is gaining in popularity as a possible solution to this problem. And there are many platforms where they're trying to implement a kind of sharding, including the ones that you see here and many others. And these are in various stages of research, development, and testing. One of the things that you need to be concerned with in a sharding implementation is that it requires that the transactions are distributed evenly across the shards. And this is called load balancing. Current proposals rely mostly on randomization for load balancing, and this can lead to frequent cross-shard transactions, which are expensive computationally, and they may also require some communication between shards, which will incur some latency. The solution that we propose here is to use dynamic transaction pricing to give the agents an incentive to use the ledger more efficiently. So transaction fees is something that already exists in ledgers, and their purpose is to give an incentive for validating transactions and to distribute the costs of maintaining the ledger. And there is some inherent flexibility in these fees, and so what we'd like to do is to use this flexibility to create incentives for the agents to use the ledger efficiently. And the objective is to design a transaction pricing policy that's going to lead to this result. Before discussing the pricing policy, let's talk about a few useful concepts and notation related to sharding. So in conventional blockchains, we think about transactions being validated in a sequence where you have a time axis, and 1 unit of time represents the approximate time required to validate a transaction. Sharding opens up another dimension where you can validate transactions in parallel, and a transaction in this case can occupy one or more shards. In general, you have many transactions being submitted, and each one of these can occupy some moment in time or a shard on the ledger. And we call this the transaction pool. So we have a set of shards, and for our purposes, we're going to assume this is fixed, but this need not be the case in general. We only require that it's fixed for the short term. The transaction cardinality is the number of shards used by a transaction. And another useful metric is the shard usage, and that is the number of transactions using a shard divided by the total usage. And in this case, the total usage can be thought of as the number of occupied grid squares in this diagram, which is 12. And then the shard usage is the number of transactions using the shard divided by that number. So on the top we have 4 out of 12, in the middle 2 we have 3 out of 12, and the bottom 2. Next, we can define loading for the shard, and that's simply the amount above optimal usage. So we don't care if there's no loading or if it's below loading, but this top shard, which has a little bit more than optimal, gets a loading value, which is this usage subtracted by the optimal, which is 1/12. So we can use this to visualize a couple of things that can go wrong with sharding. So one of these is when all the transactions have a high cardinality. Even if they're well balanced, you're losing efficiency by using 2 shards per transaction. In the middle case, we have the other side, which is where all the transactions have low cardinality, but they're imbalanced. They're all stacked into only two shards. The ideal case is on the right, where you have a low cardinality for all the transactions, and they're evenly distributed across shards. So that's what we would like to incentivize. So let's try to quantify this with a few metrics. First of all, a transaction is a transfer of tokens between agents, and the amounts can be represented as a vector that has m elements. And the cardinality is the number of shards used by a transaction. That can be thought of as the number of non-zero elements in the vector. Once again, the shard usage is the number of transactions that use a shard, divided by this number of occupied grid squares, which can be also calculated as the sum of all cardinalities, as you see here. And then again, the shard loading is how much above optimal usage we have in each shard. So the transaction shard balance can be calculated as the sum of the loading in each of the shards used in the transaction, and 1 minus that. So that means that this is going to have a maximum when the transaction does not incur additional loading and actually contributes to a balanced ledger. This sets up the most important metrics for this work, which is the transaction efficiency, and that's going to combine a couple of the ones that we saw before. So the transaction shard balance divided by the transaction cardinality gives us a metric that lies in the interval 0 and 1. So it's maximized when this transaction has a cardinality 1 and is not contributing to the imbalance in the ledger. We can also calculate a total shard efficiency of the transaction pool, and to do that we just sum over the balance for all of the shards, and we divide by the mean cardinality in the transaction pool. And what we did here is we have some expressions that translate the throughput to quantities that are easily measurable by the agents. Just to give a little bit more intuition, let's look at some examples. So in this case, where we have high cardinality transactions that are balanced, if we calculate the balance, we simply take the usage, 3 out of 12, minus the optimal usage, which is 1/4, and we have 0. We sum that over the 4 shards. 1 minus 0 is 1, and the mean cardinality is clearly 2, so we have a shard efficiency of 1/2. And the other case, we can calculate the balance, which is for these 2 shards is 4 out of 8 divided by a total of 8, and we subtract that from the optimal, which is 1 out of 4, so we get 2 times 1/4, which is 1/2. 1 minus that is a shard balance of 1/2. The mean cardinality is clearly 1, and we get a shard efficiency of 1/2. So in both cases, we get a kind of intuitive result that the ledger is being used at about half capacity, but we can measure this different quantities in a single measure. And so we're going to use this measure as the basis for the pricing policy, which looks like this. So we have the transaction price, which is a function of a transaction and the transaction pool. It starts from the nominal transaction price, and this can just be the incentive for validating transactions that you already have. And we add to this a small surcharge that can be weighted by some arbitrary parameter. And here we have the transaction shard balance. Because we want this price to be low when the efficiency is high, we take 1 minus this quantity, which is the transaction shard efficiency. We give one more parameter here, and this parameter can be used to have an additional penalty on multi-shard transactions. For example, if these incur latency, which was not included in the model so far, this might be a motivation to further penalize these transactions. So what we've seen so far is from the point of view of designing the ledger protocol and the pricing policy. And now let's look at how agents might respond in this context. So let's consider a network of agents who transact with each other, and they have tokens in one or more shards. So the edges in the network just represent who the agents would like to transact with. So over time, an agent, the requester, requests a transaction from one of its neighbors, the sender. And when doing this, will request a shard in which to receive the transaction. And this decision is based on, because there's going to be a price associated with this transaction, but the fee is paid by the sender. And the requester then, because they would like the transaction to be fulfilled, they would like to minimize the expected transaction fees. On the other hand, so then the sender selects a shard in which to send the transaction, and the sender does pay the transaction fee. So remember, all these fees are getting paid to the validator, not to each other. And since the sender does pay the transaction fee, its goal is going to be to minimize both the current and the expected future transaction fees. One of the assumptions underlying this work is that these agents are not just thinking in the short term, but they're thinking long term. They don't want to minimize only the current fee, but the long-term expectations of fees in the future. So this transaction is then added to the pool. So based on this, let's develop a model for how agents can choose transaction shards. So let's suppose that agent requests based on a distribution over the shards, where each of these entries is positive, non-negative, and they sum to 1 as in a normal probability distribution. Similarly, the sender selects a shard to send according to a distribution. From this, we can express a couple of useful quantities. For example, the expected transaction cardinality can be written as follows, where this matrix is encoding what happens when each pair of choices is made between the requesting and the sending shard. So if they request and send on the same shard, then the cardinality is going to be 1, so you get this diagonal of the matrix. But if they send and request in different shards, then the cardinality is 2. And if we sum all of these possible outcomes up, we get an expectation for the cardinality. In a similar way, we can get an expected shard balance, and this time the matrix is encoding the loading on the ledger that is imposed by this choice between the sender and the requester. So if they request and send in the same lane, then the loading only affects 1 shard. But if they request in different lanes, then 2 shards are affected, and that's indicated here. So we can then combine these two to give an expected transaction efficiency, and that is going to be the balance divided by the cardinality, as we saw earlier, and this matrix encodes this quantity. So now you just have each of the ones shown previously in the numerator and denominator respectively. So we see what happens when they send in a request in the same shard and when they send a request in different shards, and this gives you an expression for the expected transaction efficiency. And because the price was based very closely related to the efficiency, this looks almost the same, the expected transaction price. And if we assume that, for now, if we assume that alpha is equal to 1, it's exactly the same quantity. So the agents will choose shards to minimize their expected price over the long term. And this can be achieved with an optimization problem where they would like to minimize price, which means they would like to maximize this quantity over their distribution, of their shard distribution. And so they're going to basically update this when they get new information. And this happens similarly with the receiver and the sender along each edge in the network. These problems can be solved readily using linear programming, and the problem size is not very large because this matrix is just m by m, where m is the number of shards. So let's look at what's happening in the bigger picture. We can write the expected shard efficiency of the entire network, which directly relates to the throughput, as a summation over all edges in the network of the expected transaction efficiency. And the assumption here is that the transaction rates on each edge are roughly the same, but that's only used to simplify the analysis here. If we observe different rates, we could simply insert a rate coefficient here that would weight them by the observations. So now let's suppose that an agent updates its shard request distribution from another agent from wij to wij prime. So this is going to change the expected future transaction fees, and we can simply do the subtraction to get the quantity, which is the expected change in price. And in a similar way, we can look at the change in expected shard efficiency, which relates to the throughput, as the new expected shard efficiency minus the previous one, which involves summing over all edges in the network, the new minus the previous. But since we only have one update here, this actually is only the only positive term is from the updated edge, and we get exactly the change in price that was experienced by the agent along the edge ij. The symmetric case holds for the sender without showing the details. So what we see is that the change in price is exactly the same as the change in the overall shard efficiency. And this is a very useful result, as well. Show what we actually did here was quite a simple proof of what's called a potential game in game theory. And that's simply when there exists a function that takes all agent actions, such that when any agent takes an action, it changes its utility function by the same amount as this potential function. That means that every action that an agent takes that lowers its expected price is going to increase the shard efficiency of the network and thus the throughput. And a particularly nice property of potential games is that when agents use best responses or even better responses, that means anything that improves their outcome, and all the agents are doing this, then the potential game will result in convergence to a Nash equilibrium. And that is a state in which no agent can improve their outcome by changing their actions. So that's a nice clean result, but there's one assumption that we made here that we need to look more closely at, and that is that this update on the distribution for the requester, it actually used information from the distribution of its neighbor that is not necessarily available, because the agents may not know the distributions. That's kind of personal preferences, so they might not know that. So they need to estimate this distribution, but that's going to turn out to be okay. One more thing is that while this gives them a probability distribution with which to request on the shard, so you could implement this as a randomized strategy that's actually just preference, so it's not going to introduce non-determinism on the ledger. But it may be more practical to use a deterministic shard choice, and this would be analogous to a pure strategy in game theory. So if we make these two modifications, we can write a new update rule, which instead of maximizing over all distributions is maximizing only over these pure deterministic shard choices. And instead of using the true distribution, which they don't have access to, they're using the estimated distribution based on observed transaction history. So as I said, this is actually turns out to be okay because there's another important result in game theory. And just to highlight this, so this is actually a slightly simpler computation. It just means you should find the maximum element in this vector. And that's even simpler than the linear programming from before. As I was saying, this there's a property in game theory that's known as fictitious play, and that's exactly when you are taking actions against the estimated, so the empirical distributions of strategies from the other agents. And that's exactly what we're doing here. And so this has been proven to result to convergence to a Nash equilibrium over time. So this is kind of the result that we wanted. We have convergence to a high throughput state, and based on computations that are cheap and use available information. So let's look at what happens in a few simulations. First, on a 20-agent ring network, where each agent is transacting with both neighbors. And we'll compare a randomized sharding, which represents kind of a typical implementation, to a congestion pricing, where they're only using the shard loading information and not cardinality, to the proposed pricing policy based on efficiency. And then I'll look at a slightly more complicated case using on 100 agents, with 8 shards, and the previous one is using 4 shards. And I'll compare randomized sharding to efficiency pricing. So these are the results for the randomized case, and I'm going to describe what each of these panels shows. So these are 4 metrics. The first one is showing the usage of the shard, and there are 4 colors here. They're not, if you can see them, they are the usage in each shard. So the way the simulation is set up is that the transaction pool starts as being empty. So what we have on the x-axis are as the transaction index. And as transactions are submitted, they are randomly assigned to shards, both the request and the sent shard. And then since they are random, eventually they kind of fall into an even distribution, and they converge to a optimal balance, as is measured by this second plot here. The balance converges to 1. However, the randomization also results in a high cardinality, almost 2 on average, and so the resulting efficiency is about 50%. If we then look at a congestion-based pricing, we can get a slightly better result. So they're a little bit better at distributing the transactions, and they also gets a slightly lower cardinality, but still the shard efficiency is only about 60%. And if we compare this to an efficiency-based pricing, which is the main result of this work, then we get both a good convergence on shard usage and so the balance converges. And one more plot that I'm showing here is actually the balance of the requests, and that is actually looking at the distributions, these W distributions, how they're evolving over time as the agents are collecting more information, and they kind of are agreeing on which shard they should transact on between their neighbors. And so while this is converging, you also have the cardinality converging to 1, and this makes the efficiency getting close to 100% in this case. I think I didn't mention, so these times are the block times. So that's assuming that once you have a block limit of 10,000, and once you reach the limit of 2,500 in any particular shard, then that block is assembled and it's produced, and then the transaction pool is cleared and it's started again. So that doesn't need to be the implementation. This can work in a more general case, but it shows it's a little bit more clean to show the results in this way. So this is what you see is like 5 blocks for a total of a maximum of 50,000 transactions. In the next case, we have 100 agents that are interacting on a slightly more complex network, and this is a directed transaction network. The shard usage here, this is the randomized case, so again, it does pretty well at distributing the loads, but the cardinality is near 2 on average, so again, the shard efficiency is about 50%. And if we compare this to the efficiency-based pricing, so this time it takes a little bit longer for these shard requests to converge to a balanced state, but eventually they do, and the cardinality also manages to converge to 1, so we have an efficiency close to 1 for this case as well. So a few points of discussion and open issues. We assume that the requesting agents would like to keep the sender's transaction fees low so that the transactions might be fulfilled as much as possible. That may not be the only incentive involved for the requesters, because they might also want to accumulate tokens in shards that they use later. So this would require developing a little bit more detailed incentive model so we can understand this a little bit better. And we also assume that the senders think long-term rather than short-term. So it would be interesting to understand what the impact of some short-term transactors are on the overall throughput of the network. Finally, latency was not considered in this analysis. However, though this depends on the implementation, this approach will remain valid as long as the latency is higher for cross-shard transactions, which it almost certainly is. So to conclude, we showed a a transaction pricing policy that aligns the incentives of the agents with maximizing throughput on the ledger, and they can so you have the pricing function from the point of view of the ledger design, and the agents respond to this with computations that are cheap to compute and are based on information that's available. So I mentioned some of the next steps previously. We'd like to do a little bit more investigation of the incentive models and the latency, and then we would also like to test slightly more complicated cases and implement it on a full ledger. Thanks very much for your attention, and also thanks to colleagues Jenny Wong and Martin Abram for their help and discussions, and I'm happy to take questions.